Besides making sure that all possible factors are taken out from underneath the radical, we also have a rule that says we cannot have any radicals in the denominator. So all fractions have to have radical-free denominators. We can have a radical in the numerator, that's just fine, but it's the denominator that's no good. So in the first example that we see here, we kind of get a little bit lucky because both the top and the bottom of our fraction are perfect squares. And so since we're taking the square root, we're going to be able to do that. So it's probably not a bad idea to go ahead and split it up into separate square roots of the top and bottom. We don't have to do this. We just take the square root of it as it was, but it might be a little bit easier. On the bottom, the square root of 64 is 8. On the top, the square root of 49 is 7. And so we get an answer of 7/8. So we were able to take care of the square root in the denominator in that case. In the second example, we have a cube root for starters, so we're going to need perfect cubes or triples of numbers to get something out. But we also don't have the good fortune of having a perfect cube in the denominator. So right now it is a 5, which is not a perfect cube. But we have a good piece of fortune nonetheless in that we can reduce the fraction that we see in front of us. So 40 over 5 can be cleaned up into, since 5 divides in evenly, it'll just be the cube root of 8. 40/5 reduces to 8. And so now we need to take the cube root of this number. Now 8 is a perfect cube, so we can just take the cube root of that number, just like we could take the square root of a number we recognize to be a perfect square, like we did in the previous example. Or if we need to, we can go ahead and factor tree this. Hopefully we know that it's 2 times 2 times 2, or if we go the longer route, 4 times 2 equals 8, and then 4 breaks into 2 times 2. And so now we have a set of 3 2's underneath a cube root symbol, which means it'll come out as a perfect cube 2 on the outside. For the last one, we've got the 4th root of 2 over the 4th root of 32. So even though these are written separately, unlike how this first one was written, we can still reduce this. So I can divide the top and bottom by that 4th root of 2, or if it makes sense for us to see it a little better, it's the 4th root of 2 over 32. So this time I'm taking it from being 2 separate roots and rewriting it as a single giant root over the whole fraction so that we can see that we can reduce this fraction. And so I'm going to end up with 1/16, and that's all underneath this 4th root symbol. So now I'm going to go back to splitting it up again. So I'll move over here. So I've got the 4th root of 1 over the 4th root of 16. Now the 4th root of 1 is just 1, since I can multiply 1 times itself any number of times that I want. So I'm going to end up with 1 on the top. And then for the 16, I can go ahead and do a factor tree. 4 times 4, and then those 4's break into 2's, which is great because if I'm taking the 4th root of something, I need a set of 4 of a number to be able to get it out. Well, here's my set of 4 2's. So the 4 2's underneath the 4th root symbol come out as a single 2 on the outside. So we get an answer of 1/2. So in the previous 3 examples, we had the good fortune of either being able to reduce away the fraction like we were in the middle one, or we had a perfect square or a perfect 4th power after doing some reducing in the last one, to where we were able to take the root of whatever number was in the denominator and then have it disappear that way. For the next examples, we're not so fortunate. So for example, the square root of 5/7. 5/7 can't be reduced. 7 isn't a perfect square, so I'm going to have some mechanism of getting that 7 out from underneath the radical symbol in order for this to be simplified. And so the way we're going to do that is we're going to rewrite this as root 5 over root 7, and then my rationalization technique, meaning making the denominator not have a square root in it, is going to be to multiply the top and bottom by root 7. Because what that does is that'll give me a pair of 7's underneath the root symbol, and so therefore 2 7's underneath the square root symbol comes out as a single 7 on the outside. And so now I no longer have a square root in the denominator, But I haven't changed the value of my fraction because I multiplied not just the bottom by root 7, but the top as well. So when you multiply the top and bottom of a fraction by the same thing, you're effectively multiplying it by 1. So we're just changing how it looks, not the value of the expression. On the top, we're going to multiply root 5 times root 7, and so we can just go ahead and multiply those numbers that are underneath the root symbol to make 35. But the square root symbol is still there because we don't have a pair of the same number underneath the root symbol, so we're just multiplying those together. And so this is the best that we can do. We might be tempted to reduce that 35 in the top and the 7 in the bottom, but we have to remember that that 35 isn't really a 35, it's the square root of 35, which is a number that's a little bit less than 6. So this is indeed the best that we can do. So again, our technique is to multiply the top and bottom by square root of 7 in order to make a pair of numbers underneath the square root symbol so that we can take it out and end up with no radical in the denominator. For the next one, it's not a square root that we have in the denominator, it's a cube root. So we're going to need to clear that. We're not allowed to have a radical in the denominator, but it's not going to be enough for us to multiply the top and bottom by the cube root of 4. And the reason is this would only give us 2 4s underneath the radical symbol. But because it's a cube root question, we would need 3 4s to get something out. So I need to multiply the top and bottom by not just 1 4, but 2 more. So that's 4 times 4. So this will give me a set of 3 4s underneath the cube root symbol in that denominator, which therefore means I'll have just 4. So whatever the root is, that's how many of a number I have to have underneath the radical symbol. And so as a result, this time just multiplying by the cube root of 4 on the top and bottom wouldn't have been enough. It would have just given me 2 4s, but I need 3 because of the cube root. Now in the top, I have this 3 that's on the outside, and then I've got the cube root of 16. But I do need to do some simplifying here. And so I can go back to 16 being 4 times 4, and then I can factor tree these 4s into 2s. And so here we can see that we can simplify the cube root of 16, and I can take out a set of 3 2s. That'll come out as a 2. That'll multiply the 3 that we already have on the outside. 3 times 2 is 6. So we're going to have 6 times the cube root of, don't forget we have this leftover 2 here since we had 4 2s and we only took a set of 3 out. So 6 times the cube root of 2 all over, we still have 4 in the denominator. And so we've got one last step here where we've got to reduce our fraction. So 6 over 4, since those are both on the outside of a radical symbol, they're not inside, so I can reduce. So this becomes 2, this becomes 3. So my final result is 3 times the cube root of 2 all over 2. And for the same reason that we saw earlier, as tempting as it might be, the 2's are not simplifiable because in the numerator it's not a 2, it's a cube root of 2, which is like 1.2-ish, something like that. So this is our answer. Now, there was a little bit faster way that we could have gotten to that result. So I'm going to show that here. What we did up above works just fine, but we can be a little bit more efficient if we rethink of how we approach that cube root of 4. Instead of thinking of it as the cube root of 4, and then we need 2 more 4s, we can instead think of it as the cube root of 2 times 2. If I factor tree the 4, I can see that it factor trees into 2 times 2. Well, now, to complete a set of 3 of a number underneath that radical symbol, I don't need 2 more 4s. I can instead do it by multiplying the top and bottom by just 1 more 2. So by factor treeing the 4 into 2 times 2, instead of needing to multiply by the cube root of 4 times 4 like we did here, instead I'm just multiplying the top and bottom by 1 more 2, the cube root of 2. And so what that does is, in the bottom, I have a set of 3 2's underneath the cube root symbol, so that's going to come out as a 2. And then in the numerator, I just have 3 times the cube root of 2. And you can see that's the exact same answer that we eventually ended up with, but it was just a longer route to get there. So my advice is whenever you can, if you can factor tree that denominator that's underneath the radical, do it, because oftentimes we're going to be able to reduce what we have to multiply our fraction by on the top and bottom. So in this case, we multiplied the top and bottom by the cube root of 2 instead of the cube root of 4 times 4. And so then it eliminated the need for all of this extra simplifying that we had to do later. So in the next example, we're going to be able to do the same thing. So I've got the cube root of 3 on the top. There's not much I can do there. On the bottom, I could say to myself, well, I only have one 8 underneath the 4th root symbol, so I need 3 more 8s to complete the set. Or if we rethink 8 as 4 times 2, and then the 4 as 2 times 2, we can rethink this, 4th root of 8 as the 4th root of 2 times 2 times 2. And so now we can look at that and realize we don't need 3 more 8s, we just need 1 more 2 to complete a set of 4 2's to match the root. So I'm going to multiply the top and bottom by the 4th root of 2. And so that then gives me the set of 4 that I need to have. So 4 2's underneath the 4th root symbol comes out as a single 2 on the outside. And then up in the numerator, I've got this 4th root of 3 times this 4th root of 2. So I'm just going to multiply those to make the 4th root of 6. And so I can't reduce this expression. That 6 isn't really a 6. It's a 4th root of 6. And so this is my result. So again, this is a much more efficient way of getting to the answer than if we were to multiply by the 4th root of 8 times 8 times 8 to complete the set. We would just have a lot more simplifying that we would have to do. So finally, for the last one, we're going to see the same sort of thing. So I'm going to split this up into the cube root of 4 over the cube root of 25. But I'm going to rethink that 25 as being 5 times 5. The top doesn't matter, I'm just going to leave it, but the bottom is going to be the cube root of 5 times 5 instead of 25. And so what I can see is I don't need 2 more 25s, I just need 1 more 5 to complete a set of 3 5s. So I'm going to multiply the top and the bottom by the cube root of 5. So that gives me 1, 2, 3 5s underneath my cube root symbol in the denominator. So that comes out as a single 5. And then up in the top, I'm just going to multiply those two. So I get the cube root of 5 times 4 is 20. So it really, really helps if we rethink those denominators. Instead of saying I need 2 more or 3 more of that particular number, to factor tree it and then realize that there's a much smaller number we can multiply the top and bottom by to avoid having to do a lot of simplifying like we had to on this first one up here in purple.